Welcome. This video is recorded for mainly for the Sustainable Ground Management course at the Department of Civil Engineering and the Indian Institute of Technology in Madras. The course is offered by Professor Ilango Lakshmanan, but also for the student here at Florida Gulf Coast University. So this is just one lesson. The course is called Sustainable Groundwater Management. And in this lesson, what you will be able to do by the end of this lesson is understand like what do we mean by the term like groundwater budget myth, and accordingly the concept of groundwater sustainability. And then we will apply these concepts to like a case study in Hawaii to operationalize a sustainable groundwater management policy in Hawaii. And then we will briefly talk about a similar project here in South Florida where we also implement these concepts to enhance groundwater climate resiliency in South Florida. So let's just get started, yeah? So let me start by just like something to stimulate your thinking. Groundwater sustainability. What do we mean by groundwater sustainability? Is this like some generic and utopian term, or it has like a clear definition and it's something that we can quantifiable basically? So I will take you like step by step to understand this concept of groundwater sustainability, but let's just start with something called the groundwater sustainability, like a call for action. So this was like a statement in 2022 where a group of scientists, practitioner, and expert calling for action to ensure the groundwater will benefit society now and into the future. And this goal basically it has uh, three action items. So the first action item for example, as shown in this image, is like just to put spotlight on groundwater sustainability. That's the first action item. The second action item is to manage and govern groundwater sustainability. And the first action item, for example, this also build momentum towards the 2022 UN World Water Day, which was entitled "Groundwater Making the Invisible Visible." Yeah. The second action item in this call was managing and govern them to manage and govern groundwater sustainably from local to global scale by applying the guiding principle of groundwater uh, sustainability by 2030. Yeah. And the third action item was like to invest in like stressed aquifer. That was the first action item. Okay, so now let's just focus on the second action item, which is to manage and govern groundwater sustainability from local to global scale. And let's focus on like not global and like local and regional scale. Like how could we manage groundwater sustainably at like local or regional scale? Uh, so let's just look at an example here. So that's the question, like how would you estimate groundwater sustainability in your like county, for example? Yeah. So that's my question to you. Like you work in an engineering firm or like in a state like in district office where you are responsible for managing or like regulated the groundwater resources, and you supervisor told you, I want you to estimate groundwater sustainable yield in this county, like in whichever your county is. Yeah. So how can we do something like this? We first need to define what do you mean by sustainable yields that you want me to estimate. Yeah, so that's what we need to define. So one definition, the sustainable yield, if this is this is my groundwater resources, yeah, like here's your water table, and this is how much pumping, yeah. So basically somebody the amount of water that I am pumping is equal to the amount of like recharge. So you have precipitation, and this precipitation will result like you have some rainfall here, and this some of this water will evaporate, some will be used in evapotranspiration uh, in the surface or in the root zone or in the soil will go through evapotranspiration, and the remaining amount will infiltrate and recharge the you'll have like your groundwater table. So somebody will tell you if the amount of pumping, yeah, is equal to I am using the groundwater resources sustainably. That could be a definition. What do you think? Do you agree with this definition? Okay, let me tell you this definition again. So here I have certain amount of water which I will extract, which I will pump out. Okay, or abstraction. Yeah, so if the amount of pumping is equal to the amount of natural recharge, like how much water will come and recharge this aquifer, then recharge is equal to abstraction. This then I'm using this water sustainably. So now is this like a good definition? Well, the answer is no. This is not a good definition. This is not sustainable. Like this is not a sustainable yield. This is actually what is called the groundwater budget miss. Why we call this the groundwater budget miss? Because unfortunately, when you not fortunately or unfortunately, but when you pump water out, you are not necessarily extracting water from storage. When you are pumping water out, what you are doing, you are there is something called like groundwater capture. You are basically capturing this water from other source, not necessarily from storage. So you could be capturing this water from like surface water, or so like for example, when you start pumping, uh, spring discharge, for example, will that will be discharge like through spring. Submarine groundwater discharge, which is important. So as a spring discharge is important for beneficial use and for terrestrial groundwater dependent ecosystem. Submarine groundwater discharge, they are very important for marine ecosystem. So basically, when I start pumping, what will happen? Submarine groundwater discharge will decrease, uh, water level at the stream will drop, and this is called capture, groundwater capture. And my groundwater level might not even change, like because I'm not changing the storage, I'm just capturing this water from somewhere else. So obviously this is not a good definition. So sustainable yield should be defined basically not just like as natural recharge. The amount of pumping should not only be equal to natural recharge, but natural recharge plus induced recharge, like your total recharge. Induced recharge, this is like the recharge, like groundwater capture. So it should be like natural recharge and groundwater recharge. So basically, you need to account all. If you subtracted this, then you will get like what's called the sustainable yield. Uh, but again, as I will show you later, when you abstract water, it is not only about like the water quantity. There are water quality issue, because when you abstract water, you could cause like salt water intrusion. Even if it is like, even if the amount of water that I'm extracting is equal to like the natural and induced discharge, like I'm accounting also for groundwater capture and induced discharge, I could cause a salinization problem. I could cause salt water intrusion for coastal aquifer. I could also affect water quality through mobilizing heavy metals. Like when I start pumping water, I could contaminate the water by arsenic, for example, by mobilizing some heavy metals. I could affect groundwater indirectly, like I abstract this water, I use it for agriculture, then the water will come back with loaded with nutrients and pesticides. So I could also affect the groundwater indirectly through like infiltration of contaminated water. Yeah, from agriculture. Yeah. So basically, so the definition of sustainable yield as I need like just as pumping would be equal to natural like recharge and induced discharge like need to be accounted for is not sufficient because a more general definition would be when you abstract that would be more general definition. Yeah. And so here, let me just show you that these are like the different factors that we call them like the eight pillar of groundwater sustainability. So this eight pillar, they consist of like natural groundwater system like recharge rate and storage condition, like how much water rates are getting recharging your aquifer and what are the storage conditions of these aquifer, because different aquifer like a karst aquifer will have different storage conditions than like sandstone like aquifer, than like uh, sediments and gravels. Yeah. Discharge rate and environmental flow. So we need also like the groundwater system. It is like discharge rate, spring discharge, submarine groundwater discharge, and these like environmental flow, like water, the ecological water use. Yeah. Water quality, as we discussed, like we need also to pay attention to water quality. So water quality, this will include like point and non-point sources and of organic and inorganic contaminants from like emerging, like such as contaminants of emerging concern like PFAS, like salt water intrusion, mobilization of heavy metal, and so on and so forth. And hazards, as I mentioned, like when you start pumping, you could cause subsidence, which could affect the integrity of building, which will make the whole region more susceptible. So sea level rise and like hurricane damages will be more severe because you have sea level rise from one hand and you have land subsidence from another hand, and that could make hurricane impacts and other hazards could be like the opposite, could be like flooding, like in South Florida, for example, like at Florida Gulf Coast University, you have a very shallow water table. So if you have a high water table, that could cause like water logging issue and it could cause like flooding issue. So that could exacerbate or like make flooding issue worse. Yeah. So this is called the natural groundwater system. But on the top of this natural groundwater system, so these are four like main factor. On the top of this natural ground system, there are like this is not faculties, these are facilities and technology. You have like, so this is a typo here. Like this is like you have facilities and technologies. This is like pumping, injection, station, conjugative use of groundwater and surface water, managed recharge, monitoring and storage network, water like transfer project, treatment, desalinization, and groundwater substitution, for example, using desalinization, this water distribution network. So you have also, yeah, let me just correct this. Then this is not, this is, this is facilities. Facilities. That's called facilities, not faculties. Yeah. So, okay. Uh, so you have all like these facilities that you need, like when you evaluate this groundwater sustainability, you don't only look at the natural ground system, but you need to take into account like this infrastructure pumping, like energy, for example. Are we pumping from deep well or shallow well and things like that? Yeah. All this. So we have, this is a quantity of extractable groundwater or like the groundwater stock. So you need to account for these 5 factors, and this is called like aquifer performance factor. Now, on the top of this, on the aquifer performance, like how your aquifer is performing, there are like institutional system. So this institutional system, this include like legal and institutional constraints. So this legal and institutional constraint could, for example, include like administrative framework, water right, restriction on production and well location, well depths. So these are like certain policies. Restriction on specific activities, like we don't need like some crops that require heavy irrigation, such as sugarcane, and we will replace this, for example, with organic farming for fruits and vegetables, things like that, or rice irrigation to be substituted with some other like strategic crops, something like that. Yeah. So there could be some restriction on a specific activity, and program and incentives for like water in efficiency, conservation, uh, also regulation on the connection between surface water and groundwater and their conjugate use, like in the, for example, in California, Sigma, like this new policy for sustainable groundwater management, Sigma, sustainable groundwater management, where it clearly stipulates that surface water and groundwater, these are not two distinct features. These are one connected system. These are not separate systems. So you could have policies that would emphasize this, the interconnection of these systems, and that these two systems should be managed together. Yeah. Or groundwater sustainability policy or no overdraft policy. So all this, wherever, like here in Florida, for example, like groundwater is managed through like several groundwater management districts, groundwater policies. Yeah, so all this needs to also be taken in consideration, like the legal and institutional constraint when you evaluate this groundwater. And then also the socio-economic system. So the socio-economic system, you have like societal value. So you have instrumental value, you have that like the environment is important for human use, and you have like intrinsic value, like the environment is important regardless of human use. You have relational value, you have aesthetic value, you have several types of values. Uh, like resilience, like indigenous right, like consensus, and like sometimes this societal values and preference, sometimes they could align, sometimes they could contradict and compete. So you have to identify these different societal preferences, especially when you have competing interests and diverse, not just diverse, but also competing interests. Yeah. And like the last pillar of aqua is of ground, of, like you need to consider when you evaluate the groundwater sustainability is economic feasibility. So like pumping costs, groundwater substitution costs, like for example with uh, desalinization, induced like recharge costs, like when you do induced recharge and you artificially recharge this aquifer, or even hydroeconomics, as I mentioned, like an evaluate like not just the cost of groundwater, but what's the best use of this groundwater. Is it better that we use like the best use of this groundwater to do like sugarcane farming, for example, or is be more useful for everyone and even more profitable to replace sugarcane farming with organic vegetable and fruits, like in Hawaii. And most of the food like get exported from outside. Would it be more feasible to use these limited amount of land and groundwater in sugarcane farming, or is better to maybe use organic vegetable and farming? So these two are called like aquifer governance. So we have several factors. Some are aquifer performance and some are aquifer governance. And when we evaluate groundwater sustainability, we look at these different factors based on the study objective. So what I will be showing you, I will show you like just some like this what I talked about, like policy and management transition for groundwater sustainability. So giving this factor like safe yield is pumping is constrained by natural recharge. I talked about this. Sustainable yield, pumping is constrained by natural induced recharge. You have to account for groundwater capture. Sustainable groundwater development is like pumping. You pump the water without adverse hydrological, environmental, and socio-economical consequences. That would be sustainable groundwater development. Sustainable groundwater management is that so these are like those 8 factors that we considered before, like without hydrogeological, environmental, and socio-economic consequence, like this aquifer performance and governance factor. Sustainable groundwater management is that you do this is similar to sustainable groundwater development, but it's sustainable groundwater, but with participation and adaptive governance. So, because I could do this assessment in a kind of like a top-down technocratic approach, so the government will just say, okay, this is the best policy for everyone, or this could be through like a democratic and like a participation process, which we will talk about later. Yeah, and adaptive governance. We'll talk about this later. So I will show you 2 case study of applying this principles of sustainable groundwater management in 2 case study. Actually one case study, not 2 case study, because one case study is in Hawaii, and the other case study is still work in progress here in Florida, in a project that is funded by the U.S. Environmental Protection Agency, U.S. EPA. Okay. So let's start with the Hawaiian case study. So the Hawaiian culture shapes the Hawaiian culture uh, shapes the state's sustainable groundwater management policies here. So here, this map is for the USA, and this map is like for water rights. So you see here, this color. So some state has what is called like pure riparian, like landowner, and some state like that would be the blue, and some state has like pure prior appropriation. So what does this mean? So like in case you're not familiar with this term, pure riparian means like landowner. Like so, if I have a land and this water sources pass through my land, so I have uh, access like to this, like I own this water, or I have like access to this water, like landowner has the right to the water. So if this land pass through my land or pass under my land, so I have right to this water. That's like pure riparian landowner. The other form of policy is pure prior appropriation. Pure prior appropriation is the first appropriation right, like the first beneficial user has the right of this water. That's, for example, if I'm the first beneficial user, then I have the right of this water. And then you have everything in between, like you have regulated riparian and prior appropriation, formerly riparian. Some state, like in California, you will find like mixed prior mix of this one and of this one, or some states they shifted from prior appropriation, like from this one to form, like from repair appropriation. So you have, that's all the USA is like this one, except one state here, which is Hawaii, which is neither, does not follow any of these dicterian or like anything in between. So what is Hawaii? Hawaii is other doctrine. So what is this other doctrine in Hawaii? That's not like pure riparian landowner or pure prior appropriation first user and one state in Hawaii. So this other dictorian is called like the state water code, based on Hawaiian concept of shared resources and establish the groundwater sustainability policy in Hawaii. So this other doctrine, which you see in yellow here, this is called like the public trust doctrine, which you can read it here as state water code shall be held in public trust and like liberally interpreted to obtain maximum beneficial use of the waters for the citizen and the state. So basically, this is called like a public doctarian trust, where it treats these groundwater resources as a common pool resource. This common pool resource should be managed to maximize beneficial use of this water for the citizen of the state. So it's a very different dictorian. Yeah. So this water dictorian, it has like 4 critical pillars. First is like the Hawaiian rights. So it account for like the Hawaiian rights. I mean, I'm not gonna go into the details of this, but the protection of like fish and wildlife and the ecological beauty and the waters of the state, like this public trust doctrine, and that we manage the water as a common pool resource. So these are the four critical pillars for giving like this public trust doctrine is governed by this four critical pillar, and it is governed by a policy called like the sustainable yield policy. So basically, this sustainable yield policy, and this was in the State Water Code that was enacted in 1987. This basically policy say like the maximum rate of water sources without like you can pump like what is sustainable yield is defined like how much water is the maximum amount of water that I can pump from this water sources without impairing the utility or quality of this water resources, like without like impairing this aquifer performance factors. Yeah. So basically, this is how this sustainable yield policy is defined in Hawaii. Yeah. So you have like this established policy defines the sustainable yield, okay, of the state. So now what we want to do is like we want to estimate the sustainable yield. Like how could we estimate the sustainable yield? What is this maximum amount of water which we can extract without impairing the utility of the quality of this water sources? So uh, in Hawaii, this sustainable yield is estimated using something called the RAM2 model, like robust analytical model. This model is an analytical model derived from Darcy law from first principles, and basically this model uh, is very simple. It's only you only have two parameters. So you see, it's like a very like you can estimate the sustainable yield for each administrative unit through only like two parameters basically. Uh, which is a very like simple model. So here, this is sustainable withdrawal, like this sustainable yields that we want to estimate. Sustainable withdrawal is a function of H0. So H0, these are the pre-development head, like head before pumping, like before any pumping, the pre-development head. HE, this is the current head level, and I, that's recharge. So basically, if we know what's the pre-development head, we get the current head and recharge, then we can estimate the sustainability, like how much water we can pump out from this unit without causing impairing, like without causing a harmful effect. Okay, so this I mean that's a great model. It's very simple. It's easy to use. Only one unknown parameter is like this one, so it has only one unknown parameter, like the pre-development level, and then you just need to find like these two parameters, the recharge and the current head. That's like the advantage of this. Like the limitation, it does not account for spatial distribution. So it's just like a lumped model. Like you only get one number for an whole like administrative unit. It does not account for administrative units. So that's basically like the drawback of this, and it could underestimate like also drawdown. Yeah, that's the main. It accounts RAM to account for saltwater intrusion, so that will also account for saltwater intrusion. So we thought like, okay, why don't instead of like this very powerful model is very useful, but why don't we also for like the most important aquifer in Hawaii, which is Pearl Harbor aquifer, which serve about half of the state population. Why don't we use a numerical model and estimate sustainable yield like using a numerical model which is spatially distributed? Yeah, so it accounts for different like spatially. So here, this is the eighth island of Hawaii. Here, this is Oahu, where the state capital Honolulu is, and you see this is the Pearl Harbor aquifer. See, it covers most of the Oahu capital and serves about half of the state population. Uh, you see here, these are four different administrative units. So these are four different. Two estimate is 22 million gallon per day. The current pumping is 15 million gallon per day. For this unit, for example, RAM2 estimate is 94 million gallon per day. The current pumping is 84. For this unit, RAM2 estimate is 52. The current pumping is 42. For RAM2 estimate is 14 million gallon per day, and the current pumping is 12. So sounds good. Like that sounds sustainable because RAM2 estimate for this aquifer, it tells you that sustainable yield is 182 million gallon. You can pump up to 182 million gallon without causing like adverse impact. And the current pumping, like if you 15 plus 84 plus 42 plus 12, that's like 117. So that sounds good. Like we are below this current pumping. That is true if this number, if this estimate of the RAM2 is accurate, which we will show you now, it is not very accurate. So let me show you how accurate or inaccurate this is. So like in this figure, what you will see here is I will project these current estimate like this 115, 48, 42, and 12. Each pumping, like, so this is here, this is the pumping well, like this is how the current pumping rate. So here you see more pumping, here you see less pumping. These different feature shape like well like different types of well, like a port of water supply federal well, others these are mainly some private well. So if we projected this into the future, you see a lot of these well. So basically this is a mid-century projection to 2065. So if we projected this to 2065, you will see just like the current pumping. I'm not doing anything. I'm just saying like the current pumping, I will continue with this pumping rate until 2065, and I will see how much salt water intrusion I will get. So basically, I will see all this will be salinized, all these red guys here, all these red guys here, all these. If we just projected the current rate to the future, how much salinization we will get. Now, if we started to account for the impact of climate change, so impact of climate change on recharge and sea level rise, projected fresh water, that will be like 86%. I will lose about like 46% of my fresh water resources, like about half of my fresh water resources. You see, like salinization will not, like here only salinization is happening here, but here you will see salinization will also like happen here in other parts of the aquifer. Yeah, in other parts of the aquifer. And if we just look for changes like climate change, is this like we are uh, suboptimal, like we are not like doing any water, like the projected groundwater will be only 61 and you get more salinization. Yeah. Okay, so how can we mitigate this? How can we mitigate this impact of climate change? Uh, so two ways we can mitigate this. One way is that we can optimize this pumping, like we can use simulation optimization to optimize, like see where to pump from. Another mitigation is that we can do some watershed restoration using nature-based infrastructure, which I will show you how to do this. Okay, so how to do this? Yeah. So again, like how to do this within context of sustainable groundwater management, like how to estimate groundwater sustainability or sustainable yields. So remember and account for these like 8 factors that I mentioned. Like to do this, we like here is what we are proposing, like to go from safe yield to sustainable yield to sustainable groundwater development to sustainable groundwater management. In our evaluation, we need to account for 3 things. This modeling, we need to account for surface water and groundwater systems. So these two are one, account for groundwater dependent ecosystem. So water used for human and ecological use. And we need to account for human activity. So this is called like multi-process modeling. So in addition to this multi-process modeling, we need to do this transparently. We need to have some like, what do you call it? Like epistemic humbleness or epistemic uh, humbleness. Yeah. We need to account that our knowledge, yeah, is is incomplete, and we don't know. So we need to account for the uncertainty of our knowledge. Like we, not everything we know is like, there are certain things we know for sure. There are certain things that we are uncertain about, and there are certain things that we don't know. So we need to acknowledge this. Like we need to have this epistemic humbleness. And that could be done at different level, like statistical and conceptual uncertainty by accounting for different scenarios for the subsurface, different scenarios for management, and for the subsurface, scenario uncertainty and adaptive management. We also need to account for scenarios uncertainty, different scenarios for climate, different scenarios for land use and land cover, different scenarios for water use and water accessibility and water usability. So we need to have this different scenario. And we need also, like, there are certain things that we will not we need to account for, especially when it comes to groundwater dependent ecosystem for adaptive management. Yeah, so for groundwater dependent, for human activities, this is where we get to like gaming and ambiguity, because human activities, these are could be different types of uncertainty where uh, we are it's not only we are uncertain, but you also have diverse societal preferences, and these societal preferences, so need to identify these diverse societal preferences. They are contradicting. You have different groups with different interests, and how to balance these interests and how to create this discussion. And that's why we need this needs to be done within a participation framework. So participation framework, it has different level. Like the least is demand driven. Demand driven means that like I'm doing it is it fulfills a societal need, it fulfills the interest of the community, it fulfills the interest of those state agency who are regulating and management this resources. So need to provide you with input so that your study or your engineering design or your evaluation will be relevant. So that's the least you can do. If you want to take this a step further, that would be collaborative modeling. Collaborative modeling is that you, instead of like, so demand driven research is that I do something, I show it to like stakeholders, they provide me with comment, I take into account this comment. Collaborative modeling is actually you design this tool with the stakeholder. So the stakeholder and the researcher or the engineering firm or whatever will design this tool together. Yeah. And then another social learners and just like wider participation. So basically, that's how we can move from safe yield to sustainable yield to sustainable groundwater development and sustainable groundwater management. Let me talk a little bit more about participation because there are more details here. So here, this figure is modified from Pasco Carrera in 2017. And in this paper, Pasco Carrera, she introduced like this ladder of participation and type of cooperation. So this is collaborative modeling. So collaborate like discussion or co-design of this tool. And that's exactly what we did in this study. So in this study, in the study of Hawaii, this simulation optimization tool that we will use to estimate groundwater sustainable yield, we designed this tool with the state water regulators. Through workshops, which I will be talking about, we were just co-designing this tool together. And the type of collaboration, you can have unilateral action, you have some coordination, you have collaboration, and you have joint action. So it was more than discussion. We were like here, like co-designing these tools together, and the type of cooperation or like cooperative continuum, it was more than we were just like coordinating our efforts. We were just collaborating, like, so we were both working to design these tools together, not just coordination and not like unilateral action from the state water regulator or from the research group. So we were like collaboration and discussion. So that is also, when you do this with the stakeholder, you need to have a clear understanding. What exactly, where am I on this figure? Am I here with, is the stakeholder only informed, actually collaborating, or we are doing like a co-joint action? So that's one thing. But another thing that we often overlook is those stakeholders that we are engaged design with, what is their institution governance paradigm? Are they like a hierarchical paradigm, like dictate and defend, like an army, for example, where they, okay, we'll come with an engineering design and this engineering design will be implemented. That's it, with not much consultation with more general public and community? Or is it like a consultative paradigm, like inform and solicit? So also like an army. So we'll come with an engineering design, we'll not just inform it to people, we'll inform the communities. This is where we came from. Let's just solicit some input. What do you think about this design? They might give us some input. We might change it for a little bit, and then this actually, this hierarchical paradigm, this is not generally like considered for sustainable groundwater management or groundwater sustainability. We need to be somewhere here, like the institutional, like your main stakeholder, like whether like our main stakeholder here was the seaworm, the state water regulator, and the state water manager. What is the institutional culture? Yeah, what type of governance they have? So in our case, our institutional was like cooperative paradigm, partner, and co-design. So basically, like the state water managers, they do wide consultation with the wider community. And why do they do this? Because this is part of the law. This is part of the policy. It is like this policy, like groundwater in Hawaii, is managed as a common pool resource. So part of it, should be like cooperative paradigm. And then co-governance paradigms, that's even further. That would be like shared authorities. That, for example, would be like indigenous community. Like governance would be the Seminole tribes, for example, here in Florida, where they have excellent environmental stewardship, and where you basically, the stakeholder are this the actual community, and they are the actual, like they do like kind of co-governance. So you need to we have like this work is still under review, so you can check it later when it's published if you want to read more about this, like different institutional governance. But here you need collaboration. You need to see what is like where is the what type of participation, what type of cooperation, and what type of the institutional governance. So here, this is, for example, like this collaborative modeling. See, I mean, I don't know if you can read this, but once this is published, like this can solve a lot of you think of this tool, like this tool, you have a simulation model, you have on the top of this an optimization algorithms. There's a lot of details, and these details, usually as a researcher or as an engineer, you're not going to know the answer. Like the one who knows these answer are the one who are regulating and managing this resource. These are the one who knows these answers very well, including some sources of uncertainty. I'm not going to go through this, but one, you can pause this video and look at like certain sources of uncertainties that as a researcher or like are some sources of uncertainties that we were able to figure out from this collaborative modeling process. Yeah, so you can pause this video and look at these sources of uncertainty. Yeah? Okay, so the output was of this collaborative modeling was, for example, like this map here, where it was very useful. They will help us to tell us all these pumping wells. You can divide them into three groups. These pumping well, they have different water usability, so you can divide them into like this solid black and white. These are basalt rock and for use for like drinking water, which has this salinity level. But the cap rock wells, these are for irrigation, for example, of golf course or other type of irrigation, so salinity could be a little bit higher. So we were able, this is one of the output of this collaborative modeling, and then we were able to define, like develop the simulation optimization tool together. So here, this simulation optimization tool, it has like a water budget model. So this water budget model will generate recharge map giving like land use and land cover scenario and different climate change scenario. So it looks something like this. And then you have a groundwater model that will simulate, numerical model simulate groundwater flow and chloride transport. So it's a density dependent flow. In that case, it's a finite element model called like Sutra, developed by the USGS, Sutra, Cliff Voss. And then you have an objective function. So what is my objective function? I want to maximize pumping withdrawal without reducing salinization risk. So I want to reduce salt water intrusion, minimize head drop, like drawdown. I don't want the water levels to drop. Conserve the spring discharge, which is important for terrestrial ecosystem, and sustaining the submarine groundwater discharge, which is important for a marine ecosystem. So you in code, you see like all these different, has a lot of option, and you get all this information from this collaborative modeling process. Yeah. And then you have an optimization algorithm that will keep finding what is the optimal solution where I can fulfill these objectives and maximize pumping. So basically, I'm solving this as an optimization problem. I want to maximize pumping while minimizing, like not violating this constraint. And then this is like this model are computationally expensive, so you need to run this on parallel computing with maybe 100 cores or something like that. Yeah. So here, let's look at the optimal solution. So with the optimal solution, that's without any climate change. Yeah. So with the optimal solution, if I just optimize the pumping, yeah, you see here some well will be salinized. So this is in mid-century, 2065. Some well will be salinized, but overall, I could pump 30% more. I could pump 30% more by just optimizing where I could pump from. So here, this is the RAM2 estimate, for example, is 22. The current estimate is 15. The optimal is 15 here. Like here's the RAM2 estimate is 94. The optimal is 74. The current is here. But by just optimizing pumping, I could pump more. Yeah. I can pump like 30% more. Now we need also to constrain the spring discharge. So if we constrain the spring discharge, so we can pump 8% more versus like the first case 20% more. So by just constraining spring discharge, because to like the current level, so here I'm allowing the spring discharge to vary. Here I'm constraining spring discharge. So if I'm constraining this spring discharge, I still can pump more. But let's see, so this is just like by just optimizing pumping, I can pump like 8% more. Versus the one without optimization, I get like 12% more. So overall, by just optimizing pumping, like 8 plus 12, that's 20%. Yeah. So if you compare this with the other ones that I showed you earlier. Now, if we accounted for the impact of recharge, like because with recharge, one of the climate scenario, and specifically not the scenario itself, but like a downscaling method, like statistical downscaling method, shows that we will have rest charge. So with this, if I optimize up my pumping, uh, remember, in that case, I would like you lose 26% from my groundwater resources versus this one, I will only lose 12%. So I can pump like 150 more. If I accounted for sea level rise, remember the sea level rise scenario, I would lose like 46% of my groundwater resource. Here I will only lose 15%. So I can pump like 99 million gallon more. So you see, by just optimizing your pumping, you can mitigate some of this impact. So you can reduce like 46%, you can reduce it to 15% only, loss of your fresh groundwater resource. We also, groundwater is equally important for ecological use. So I will not go through like this slide. I will pause, you can pause the video and like please see here like these are groundwater dependent ecosystem. You see like different groundwater dependent ecosystem and the impact of pumping on these groundwater dependent ecosystem. Like take this as an example, like number one, for example. So number one, like in wet forest, for example, you have these guys, like these types of tree. These are called phaerophytes, and where they tap like the groundwater level. So if my groundwater table dropped, they will not, this forest will turn to yellow. So if you see this forest like this phaerophytes, if they are yellow or green, that will tell you if they are able to tap or not tap through this groundwater. So if I go below like the root of this plant, then this will turn yellow. You can pause this video and look at these ones and the importance of groundwater for this different groundwater ecosystem and also like why these groundwater dependent ecosystem are important, like groundwater ecosystem surface. Yeah. But now, so that's why like this groundwater dependent ecosystem. So here you could have like different, we need to account for societal value and preference, because some people will tell you, you know what, we don't care about this groundwater dependent ecosystem, we just want to pump more water, we don't care about spring discharge, we want to pump more groundwater, and that's what we care about. While other people will tell you, no, we know what, we need to depend on this groundwater dependent ecosystem and also the beneficial use of this spring discharge. So you always find this two constructing like societal value on preference, like instrumental values. So the instrumental value, environment is important for human activity. Intrinsic value, that will tell you environment has its intrinsic value. So here the objective here would be, the goal here would be to enhance economic vitality and quality of life. The objective for this group of people will be maintain and improve environmental quality. So here, for example, an example for this one would be groundwater for irrigation, municipal use, and industry. An example for this one would be groundwater maintain environmental flow and stream flow. So these are two types of value. So when this consultation and this, like when you go to this relational value, like respectful abstraction. So that's very different. So that is based on connection between people and place. And the goal here is to like preserve cultural identity and environmentalist respect, like spring discharge, for example, and cultural ties, something like that. Other would be aesthetic value, that we aesthetic value is that the place should be beautiful, like so, because any engineering design, I could design something to function, like I could design a house to function, or I could add an aesthetic dimension to it. I could design something to function, but it also has like an aesthetic dimension to it. So sometimes you see place to function. While other cities where everything is, because they were designed to look beautiful. So these are aesthetic value. In groundwater, for example, like the goal would be to enhance the scenic beauty and aesthetics. That's explicitly stated in the State Water Code in Hawaii. Example would be groundwater protects the beauty of the place. So if the groundwater will affect the beauty of the place, groundwater abstraction, then you shouldn't do it. Other would be like equity, like that would be like fair resource distribution. So the goal here would be to account for the intra and intergeneration equity. So equity is not necessarily equity among like different generation, is that like we don't use generation or leave triples only for the next generation, but also intergeneration, like equity between different groups, like uh, uh, rich versus poor, yeah, things like that, yeah. Or so that is also like fair abstraction law. So so you need to account for this. So groundwater abstraction consider societal outcome and future generation. So for example, like in these 4 aquifer units in Hawaii, we should not cause like some of these aquifer units, they will not be for like rich people area, some would be not for rich people area. So how could you not, how can you and then public health for sure, like groundwater development practice should not like impact public health, and we talked about public water quality, like mobilization of arsenic, for example, or contamination by pesticide and nutrient from agriculture and things like this. So groundwater abstraction does not mobilize heavy metal or transport contaminant or things like this. And then like resilience. And resilience, by the way, is the way AI generate. I like this picture because AI thinks that resilience necessarily need to be through this hard infrastructure, which is what we also think. But resilience could be also through nature-based infrastructure, not necessarily like this hard or gray infrastructure. Yeah, but But resilience is like is generally defined as like you cope with crisis and return to pre-crisis status quickly. Resiliency in planning. Example would be groundwater salinization, drought, sea level rise, and so on. This definition like that would be relevant actor and groundwater users agree to support decision. The goal would be to support the decisions as part of the groundwater policy in Hawaii. This concept of common pool resources. Example would be groundwater abstraction does not create conflicts and issue because indigenous rights, this is not just like one votes among all these votes. It's according to the UN, this should be accounted for differently. So it's not just does not count as one vote. Yeah, it should be accounted differently. So indigenous rights that should be accounted for differently. Okay, so you can read more about this here. You can pause the video and read more about this. So in this case study, so we took like here in Hawaii, we look at the, let's get back like to Hawaii. So we take this like Sumida Farm. This is accounting for groundwater dependent ecosystem, human activity, and societal preference. So you see Sumida Farm here. This is like an Pearl Harbor area, and you see it's the only green area among a very densely urban area, and this is the only green area. And you have this different ground provide different groundwater ecosystem. So this is, I think, the largest watercress farm in the state. So it provide like products and employment, intrinsic value, like so that's instrumental value important for human activities, intrinsic value important for culture and community importance. So basically, culture and community importance. So this basically this is a family business that been inherited from one generation to another, and this is the only green area in the densely. Here we can use this tool to basically see the trade-off between pumping and discharge. So here, if you want to, these are basically, this is the current level. So currently we are pumping about 120, and with this 120, you will get about like 70 something, 78 million gallon per day of spring discharge. Now, if I want to pump more, if I want to pump more and increase pumping, spring discharge will reduce. So I will lose more of this spring discharge. Now, if I want to pump less, because now Sumida farms, they are complaining because they were saying that now we are getting less spring this whole region. So if we want, example, like here, so this is unconstrained solution. Here, if we want to pump less, like 60% of the pre-development level. Yeah, so then if we want to see 60% of the pre-development levels, that's how much spring discharge. 80% of the we cannot reach to the pre-development levels. This is the maximum spring discharge that we want to have. Okay, so where can we be on this curve? Like where, like how much should we pump? Like should we pump like 60% of the pre-development and then we will get that much of a spring discharge? Should we pump 80% of the spring development and we will get that much of the spring discharge? Or where should we be on that curve? Again, that is, as an engineer or as a researcher, that's your job. Like your job is to provide this figure, and then based on this figure, the community will take this figure and achieve consensus. They will say, okay, where do we want to be here? Like if we pump it that much, the, then this will affect, this will have these type of impacts and effect on this spring discharge and these other community members. So as an engineer or a groundwater hydrologist or a researcher, your job is to provide this for a community discussion. And here we are using like different types of withdrawal constrained by feasible capture, groundwater discharge, and environmental flow. Like this is the maximum that can be sustained. Sustainable groundwater management is like, we talked about this, but here we have like, now it's not only accounting for the aquifer performance, but here we are starting to account for aquifer governance. So aquifer governance, like here specifically, we are talking here about consensus yield, withdrawal bounded by the preference of affected actors through participation and adaptive governance process. So that would be, we're going from sustainable groundwater development to more sustainable groundwater management of like consensus yield. So here, this is like no use. So you'll have like no use. You'll have all the water permissive use, maximum sustained, safe mining, and maximum mining. This is the maximum. So if you consensus here, people will say, okay, we don't care about anything. Let's just pump all the water out. Or here, that would be don't pump anything. Yeah. So basically, that was one solution is like by using this simulation optimizations that can evaluate sustainable yield and optimizing pumping. The second solution which we came up with for mitigating this climate impact is through water shed restoration. So water shed restoration, we have six different land use and land cover scenario. So in this one, this is business as usual, yeah. So here you have development, like kind of the sprawler development is generally typified as like low density haphazard development sprawling around out of urban center. So you have like an urban center. Out of this urban center, you find some random or haphazard development. Yeah. Versus here, two development scenario. Like here, sprawler development. Here, like corridor development. Corridor development, that is the opposite would be development. Where you have urban planning and not just haphazard development, but urban planning with well-planned water and sanitation and stormwater drainage network and well, good urban planning. So sprawler development. And for each of these two development scenario, we tested three different watershed scenarios. So this is business as usual. This is targeted forest protection, and this is high-level forest protection. So basically, high-level forest protection, you protect the forest from invasive species, and invasive species, they could suck out groundwater. They are water thirsty, so they could suck out not groundwater. They could like reduce recharge, not groundwater. Sorry, they reduce like groundwater recharge because they increase evapotranspiration. Yeah. So by just putting some fences around and that could prevent like this invasive species from moving and spreading around, that would be like a high level forest protection. So we will see with these different level, how much could we mitigate? So remember, without doing anything, the mid-century solution is that the 117 will drop to about 99, and by just optimizing, we can pump like 32 million gallon more. So we can pump from 90 something to 132 or something. Now here, this is the corridor development and sprawler development. We don't see a big difference between corridor development and sprawler development in terms of groundwater recharge. Is about like you can, with corridor development, you can pump, I think, about 2 million gallon more. So it's not a big difference with respect to groundwater recharge, but environmental benefit is much better. Like this corridor development, environmentally speaking, regardless of groundwater recharge, this is much better. But from high level, like whether you are in this corridor development scenario or sprawler development scenario, like going from no forest protection from here to here, you can pump much more. Like you can pump 11 million gallon more. That's like about more than 10% pumping. And if you will, that would be additional. That's about 11 million year of saving for desalinization. Because if your current pumping is 117, and in the future you can only pump like 90 something, this extra amount you need to account for using. So giving like the future cost of desalinization in the future, like that could uh, about like this 11 million gallon is about 11 million, like 1 million gallon would be about 1 million gallon, $1 million per year in desalinization costs. That's about it. Yeah. So now climate change. Optimizing pumping strategy reduce the impact by mitigating saltwater intrusion. Nature-based solution enhances climate resiliency by increasing recharge. And I would like to acknowledge the research team who are helped also in preparing some of these results and slides. Yeah, the National Science Foundation. Yeah. Collaborative modeling and hydroecological human system tool support decisions. We developed this tool which can be useful for supporting decisions. Another case study here in Florida, niche-based infrastructure for enhancing climate resiliency and groundwater resources in South Florida. So this is a project collaborator, and this project is funded by the Environmental Protection Agency. So you see here for sea level rise, is expected by the end of century to be around 1 meter, and this is the impact of 1 meter, for example. So the impact of 1 meter, where will Key West go? There will be no Key West, so you will lose an island, but you'll get a new island, the island of Miami. All this would be like coastal area would be gone. You have also a changing, so sea level rise, that's the big. South Florida, especially ground zero for the sea level rise. You have a changing participation pattern. So certain area will have more recharge, certain area will have less recharge, and certain area, because you have more recharge, you will get like more flooding. Yeah. And then you have rapid socio-economic development. So again, we develop like a collaborative modeling approach. We'll assess the climate impacts. We will see how nature-based infrastructure could mitigate this and enhance recharge and ecosystem function. And then we will also do some groundwater education and outreach, and we will publish our result in a web-based platform. So that's basically like you can learn about this project here. So this is still work in progress, but this is the overall picture of this project. If you go here, you can see our recent publication, like our publication about like the access of the climate impact. I think this one we will submit this for publication soon. You will see the paper about collaborative modeling, some of the work that I presented here, and you will see some of our groundwater, like our education, not yeah, education and outreach activities. Yeah. So thank you, and yeah, just let me know if you have any question. And I kept like this video in less than